Welcome to the side Focused Learners. Go ahead and grab a hard hat, because today we are stepping directly into the blueprint room. I am your chief architect for today's explainer, and we are going to get highly practical. If you're currently studying Cambridge AS and A-level mathematics, specifically syllabus 9709, focusing on series and arithmetic progressions, you are about to undergo a complete ground-up structural overhaul of your exam technique. Seriously, I'm putting on my hard hat as an elite Cambridge Assessment International Education structural exam engineer right now. From this moment on, we are treating your next exam paper exactly like a multi-million-dollar high-rise construction project. Take a look at the digital drafting screen in front of us. Notice that structural integrity bar? It represents your mark potential, from 0 all the way to 100%. And right next to it, the construction deadline clock, representing your exam timer. Here is the harsh industrial truth that we see time and time again on the site. Most students lose incredibly easy marks on arithmetic progressions. It's tragic, honestly. They do the math, they crunch the numbers flawlessly, and yet when they hand their answers over to the Cambridge examiners, their structures just crumble into dust. But that's not going to be you. By the time we finish our work in this workshop today, you are going to possess the ultimate master framework. You will literally never lose those easy marks again, because you are going to understand exactly how to lay down an unshakable thesis foundation. You're going to learn to erect load-bearing analytical arguments and construct structural sentence connections that will easily survive the absolute most rigorous examiner stress testing out there.
So you really have to ask yourself, why do so many perfectly calculated exam answers completely collapse under the examiner stress test? I mean, imagine you are building a skyscraper. You've gone out and sourced the absolute best premium materials for the job. You have the perfect calculations for your starting number, what we called the first term A. You've mathematically nailed the exact steady gap between the numbers, the common difference D. And you've got the flawless sum formula that totals the whole thing up beautifully. But instead of carefully welding all of those premium materials to a reinforced steel frame, you just back up the dump truck and drop those numbers into a messy pile on the dirt. When the Cambridge principal examiner arrives for the final site inspection, they aren't just checking off your materials. They don't just care that you know what A and D are. They are strictly enforcing the building regulations. In our world, those regulations are the assessment objectives, the AOs. An otherwise solid, mathematically perfect calculation will instantly fail the inspection if it lacks a supporting structural framework. The examiner pushes hard on your answer. They're aggressively looking for how you interpreted the complex data, how you actually extracted it from the text, and how you justified your methodology. If you just leave them a pile of loose numbers without systematic analysis and evidence-based reasoning, the entire structure collapses under its own weight. Your mark potential drops from 100% straight to 0 in a heartbeat. We absolutely need a framework to hold that math up.
Okay, let's dive right into this master blueprint. Today, we're building this in 4 distinct phases. Section 1 covers the core foundational principles. Section 2 is the technical construction methodology. Section 3 is about preventing structural collapses. And Section 4 will be our final integrity stress test.
Let's start breaking ground with Section 1, Core Foundational Principles.
Listen, before any crane is lifted into the sky, before a single drop of concrete is poured on site, and certainly before any math is actively calculated on your exam page, you need to understand that true mathematical architecture relies completely on robust underlying concepts. You simply cannot build a high-rise on sand, right? And you cannot successfully solve a complex, high-tariff series question without deeply understanding the theoretical ground you are standing on. The theoretical architecture of series and arithmetic progressions rests entirely on 2 massive pillars: precise definitions and causal relationships. Think of these 2 things as the fast-curing cement of your exam response. When a high-tariff question actively asks you to evaluate a sequence, it isn't just asking for a number, it is drawing on established principles of systematic analysis. So you must clearly and explicitly define the parameters of your sequence right off the bat. What is the precise nature of the progression you are looking at? For instance, is the sequence adding a constant value of 3 every single time? Okay, great. But what is the causal relationship between that specific common difference and the overall long-term trajectory of the series? When you explicitly state these parameters in your answer before jumping headfirst into the calculation, you are pouring high-grade cement. You are clearly signaling to the examiner that your mathematical operations aren't just lucky, desperate guesses. They are highly deliberate, engineered choices built on absolute, unshakable precision. And right here is where we start dropping in the heavy, load-bearing support columns. Take a close look at this definition: cross-topic connections. This essentially means integrating arithmetic progressions with other entirely different syllabus areas to construct load-bearing arguments. Now, I read the Cambridge Principal Examiner reports religiously, and let me tell you, they highlight this as a massive, glaring differentiator between your average everyday builders and your master architects. Candidates who successfully reference cross-topic connections achieve significantly higher marks, period. You have to remember, arithmetic progressions do not exist in a vacuum. Maybe the sequence in your exam paper represents a rate of change, which directly ties your answer into calculus. Or maybe it models a complex financial scenario, which completely demands contextual, real-world interpretation. When you take the time to weld your arithmetic progression directly to another syllabus area, you are essentially installing a thick, reinforced steel beam right through the dead center of your answer. It becomes a completely load-bearing argument. It's so strong that examiners literally can't help but award top-band marks to it. Moving on to Section 2, Technical Construction Methodology. This is where we erect the ironwork. All right, to properly erect the ironwork of our answers, we absolutely must utilize what I call the method mark strategy. This is where Cambridge examiners actively award marks for the process itself, not just the final number sitting at the bottom of the page. If your underlying process is structurally sound, you are continuously accumulating points at every single floor of the build as you go up. But to do this, it requires a very strict, standardized construction sequence. Step 1, identify key elements. You have to systematically extract the critical data from the texts and tables provided. Step 2, apply relevant principles. This means carefully selecting the exact correct formulaic framework for the job. Step 3, execute analysis with clear working. Honestly, this is your ironwork actively being bolted together in midair. Every single mathematical step must be completely visible to the inspector. Step 4, verify results. Take a second to actually interpret the relationships you've just mathematically uncovered. Does the number make logical sense? And finally, Step 5, present in appropriate format. This means drawing evidence-based conclusions that directly answer the prompt. If you get lazy and skip any of these steps, you are quite literally leaving out crucial structural bolts. Your ironwork is going to rattle, bend, and eventually snap under the weight of the examiner's red pen. You absolutely must follow this mandatory procedural framework to safely interpret the data and secure every single method mark available to you. Let's step up to the digital drafting board for a second. I really want you to picture a scenario. Imagine two of my junior builders, let's call them Alex and Sam, and they are fiercely debating how to frame an argument for a really complex high-tariff past paper question. On the left side of our screen, we have Alex pushing for a weak frame. On the right, we have Sam aiming for a reinforced frame, but still missing the mark. Alex looks at the blueprint and says, "Chief, let's just make this easy. We list the formulas, we dump all the raw facts into a massive cement block of a paragraph, we identify the first term, the common difference, and we just brutally force the calculation through." But here's the problem with Alex's approach. Stacking all those incredibly heavy bricks of raw facts without ever checking if the specific context of the question can actually support that weight is completely generic. It's going to crack. Then Sam chimes in and says, No, Alex, we need to use shiny, evaluative words. Let's say the progression exemplifies a dynamic linear trajectory. But wait, Sam is trying to install all these decorative fancy glass panels before even bothering to cement the foundational columns. Sam is completely missing the core command words of the prompt. Both of them are building a hollow structure with zero context, and therefore it lacks the flexibility to hit those top-band scores. The classic, fatal mistake we see constantly is providing generic answers that aren't specific to the context of the question. To get top marks, you must link every single mathematical calculation you do to the specific scenario provided on the page. That, my friends, is exactly how you build a reinforced frame that passes inspection. Hold on, stop the cranes, cut the power. We've got a mandatory site inspection. Before we completely secure this high-scoring paragraph framework and pour our final layer of text concrete, I need to make absolutely sure your personal construction line is fully reinforced. I need you to subscribe to Ace the Exams. That's at Ace the Exams right now. Make sure you turn on all notifications so you never miss our weekly structural grade upgrades. Whether you are actively building a solid IGSC foundation or you're already setting up a towering A-level skyscraper, this channel is your primary grid. We provide the master blueprints. You do the heavy building. So secure that hard hat, lock in that subscription right now, and let's get back to the construction site. Okay, Section 3, Preventing Structural Collapses. Time for our site safety audit. Now, what's really interesting about this slide is that it shows us exactly where things go wrong. We need to identify the critical errors that cause catastrophic total structural failures under examiner stress testing. These are the exact specific points where students, despite actually knowing the underlying math perfectly, just stand there and watch their grades completely crumble. And listen, these aren't just guesses I'm throwing out there. These are official red tag site violations pulled directly from the Cambridge Principal Examiner reports. Number 1, forgetting to include proper format.
Presentation of information in arithmetic progressions follows incredibly strict conventions. You need proper headings, you need correct terminology, and you need clear, legible annotation. Number 2, forgetting to check that format and presentation before moving on to the next question. So many students finish the math, breathe a huge sigh of relief, drop their pen, and just walk away from a leaning tower that's about to fall over. Always double-check your structural alignment. And number 3, which is quite literally the most fatal violation of all, providing generic answers not specific to the context given. Think about it. If your mathematical conclusion could just as easily apply to any random number sequence in the world, rather than the specific financial or physical model presented in that exact exam paper, you get a red tag. It's that simple. Your building is condemned. You must always link every single point back to the given scenario.
So how exactly do we upgrade from a condemned, red-tagged building to an award-winning architectural structure? Take a look at this evaluative framework matrix. Higher-order assessment objectives actively demand that you elevate your level of thinking. If you only ever operate at the descriptive level, which means you're just stating basic facts, listing out A and D and calling it a day, you are essentially just building a basic shed. Sure, it's functional, it keeps the rain off, but it is absolutely not scoring high-band marks. To build a solid steel frame, you must upgrade your mind to the analytical level. This means using comparative connectives to actively interpret the relationships hidden within the data. But what about the true chief architect standard? What about the high-rise skyscraper? That requires you to operate at the evaluative level. This is exactly where you justify your recommendations, you evaluate alternative scenarios, and you compare different approaches. Now let's say you're mid-build and you hit a structural roadblock. Your evidence beam suddenly fails to latch onto the main thesis column of your paragraph. What do? You pull out the Peel methodology template. Point, evidence, explanation, link. You make your clear point about the progression. You rivet in place by providing the hard mathematical evidence. You supply the explanation of exactly how it functions within the given scenario. And finally, you link it firmly back to the core evaluation of the question. That is the exact engineering process of riveting your data directly to your evaluation.
And if you want to truly master that analytical steel frame we just talked about, you have to completely master comparative analysis. The blueprint here requires identifying similarities and differences, and you have to support every single claim with hard, undeniable mathematical evidence. Let me be clear, it is absolutely not enough to just say two arithmetic progressions are both growing. Who cares? What is the relative importance of their respective common differences? How do their sums to end terms actually diverge from one another over a long period of time? You have to use strong comparative connectives to draw firm conclusions about their relative importance, specifically in the context of the question asked. When you successfully identify both the similarities and the differences, you are essentially tightening the heavy bolts on your structural cross-bracing. It makes your entire argument completely rigid and unshakable against any kind of examiner cross-examination.
And this quote brilliantly illustrates everything we've been talking about. Let me emphasize this direct line from the examiner source, because it is the ultimate chief architect mindset for erecting load-bearing analytical arguments. Top-scoring candidates demonstrate evaluative thinking by questioning assumptions, considering different perspectives, and justifying decisions with evidence. This right here is the absolute pinnacle of high-rise construction. An average student just blindly accepts the formula, plugs the numbers into their calculator, and hopes for the best. But a top-scoring structural engineer, they actively question the underlying assumptions of the mathematical model itself. Does this specific arithmetic progression hold true infinitely? Or does the physical, real-world context of the problem actually create a hard limit where the sequence breaks down? By constantly considering these different perspectives and strongly justifying your mathematical decisions with clear, beautifully formatted evidence, you absolutely guarantee yourself a top-band score.
All right, Section 4, it is time for our final integrity stress test. We have poured the concrete foundation, we've erected the ironwork, and we have successfully passed the mid-build safety inspection. Before we wrap up, let's quickly recap the 3 crucial structural pillars that will ultimately hold your final grade up. First, master the format. Follow the strict mathematical conventions, make sure you show your clear step-by-step working, and safely secure every one of those method marks. Second, anchor to context. Never, ever leave a generic, hollow frame on your exam paper. Rivet your mathematical findings directly to the specific scenario they gave you and aggressively utilize cross-topic connections. Third, practice the framework. You need to drill Cambridge past papers using this exact standardized construction sequence until it becomes absolute second nature, pure muscle memory. If you do this, I promise you, your structural integrity will be firmly, permanently set in stone.
All right, I am leaving you today with one final interactive rebar stress test.
I want you to imagine a 60-second visual countdown timer ticking down right now on our digital blueprint screen. It's flashing red. You are staring at a complex data chart. You have exactly 1 minute to extract the single most high-yielding core metric needed for your construction. As that clock ticks down, ask yourself, how will you justify your very next mathematical decision with concrete, undeniable evidence? How will you upgrade your answer from a basic, flimsy descriptive shed into a soaring, evaluative skyscraper? Think about that Peel method we discussed. Think about always linking back to the context. The master blueprint is entirely in your hands now. It's time to get off the drafting board, go out there and build something that completely maxes out that structural integrity bar. We'll see you back on the site for the next explainer. Keep building focused learners.